So in this video, we're going to look at arrays as a data structure. So the most important thing to understand about arrays is how they're stored in memory. And essentially, they're stored as one contiguous block in memory. And what I mean by that is you don't have the items or elements in an array scattered throughout memory. All of the elements, items, whatever you want to call them in an array, they're all stored as one contiguous block. So let's say an array starts at memory address 100. That's a bogus memory address. You wouldn't have a memory address like that, but to keep things simple, let's pretend that we have an array that starts at memory address 100. And let's say that array is 200 bytes long. Well, then what happens is starting at memory address 100, the following 200 bytes are the contents of the array. So the array is just one huge block, and that's why we have to specify the length of the array when we create the array, because that tells the JVM how much memory it has to allocate for that array. And it's one reason why arrays can't be resized, because if they could be resized, then there'd be no guarantee after that whatever, when we added extra space on, that extra space would be in that same contiguous block of memory. So arrays have a static length, and when you create an array, there's one huge block of memory allocated for that array. So the elements of an array are not scattered all over the place in memory. Now, the second important thing about arrays is every element in the array occupies the same amount of space in memory. For example, when we created our int array, every item that we put into that array will be an integer. And in Java, an integer is 4 bytes. So every value in our int array was occupying 4 bytes in memory. You can't have an array element that occupies 4 bytes, and then the second array element occupies 12 bytes, and the third array element occupies 300 bytes. That doesn't work. Now, at this point, you might be thinking about objects and thinking, well, wait a minute, what if I create an array of strings? I mean, the strings in the array could be of different lengths, so they're going to be taking up different amounts of memory. What's important to understand when you're working with objects, not primitives, like when you're working with ints, but when you're working with objects, what's stored in the variables is an object reference. So when you create an array of objects, what's stored in the array elements is a reference to those objects. And object references are always the same size regardless of the type of object they're referring to. So if you create an array of string, what you're actually storing in the array is a bunch of object references to the string instances. And those object references are all going to be the same size. And that's why you can have an object array and store any type of object in there. It's because the object references to the different instances are always the same size. So arrays occupy one contiguous block in memory, and every element in the array occupies the same amount of space in memory. So because of that, we can easily calculate the memory address of an array element based on its index. So if an array starts at memory address X, and the size of each element in the array is Y, then we can calculate the memory address of the ith element, so array I, by using the following expression, X plus I times Y, and we're going to look at an example of this in a couple of slides, so you'll see an illustration of this. So basically what that means is if we know the index of an element in the array, then the time or the number of steps we have to do to retrieve the element will be the same no matter where it is in the array. Because all we have to do to get the memory address of that element is X plus I times Y. And that works whether we want the first element in the array, or the 5,000th element in the array, or the 1,000,000th element in the array. All we ever have to do to get really quickly to that element is do that simple calculation to get the memory address. And this is made possible because of the first 2 points, because arrays are one large contiguous block in memory, and because every element in the array occupies the same amount of space in memory. So let's have a look at this for the array we just created. So we created an array of length 7. So the valid indices are 0 to 6. And the values are 20, 35, minus 15, 7, 55, 1, and minus 22. Now, for this example, we're going to pretend the start address of the array is 12. As I said, that's a bogus memory address. You know, it doesn't matter what the number is. And because these are integers, the element size is 4 bytes. So if we wanted to get the element at array 0, well, that's equal to the start address of the array, right? Because the array starts here at 12. And so the first element of the array is actually going to have the same address as the beginning of the array. So if we want the address of array 0, we get 12. If we want the 35, we need to jump past the 20. And so if we want array 1, we're going to start at 12, and then we're going to add 4 bytes. Because we know that the size of each of these elements is 4 bytes. And so if we want the second element in the array, we start at the memory address, which is 12, and we add 4 bytes. And now we're at the start address for the 35. So that's 12 plus 1 times 4 equals 16. And if we go back to our calculation here, that's the x plus I times y. So x is the 12. I is the index, which in this case is 1, and y is the size of each element in the array, which is 4. So that's how we're doing this calculation. So if we want minus 15, we've got to jump over 2 elements. So we're going to start at 12, and this time we're going to add 2 times 4 to it to get 20. So the 15 will start at 20. If we want to get to the 7, we've got to jump over 3 elements to get to the 7. So that's going to be 12 plus 3 times 4, and that'll give us 24, and so on. And this is possible because the array is one contiguous block in memory, so all the elements are stored in one block in order, and also because every element occupies the same space in memory. If that wasn't true, if either of those two requirements weren't true, we would not be able to use this simple formula to quickly go to an element in the array. So what this means is that if we know the index of an element in the array, we can get to it really quickly, and it doesn't matter where it is in the array. I mean, if you look at array 1 versus array 6, we're doing the same calculation. And we're actually doing the calculation here as well. I didn't show it, but this is actually 12 plus 0 times 4, which is 12 plus 0, which is 12. And now maybe you can understand why array indices are 0-based. Because if they weren't 0-based, if they started at 1, we'd have to subtract 1 here. Because then we'd have 12 plus 1 times 4. That would be wrong, because then we'd get 16 for the first one. So we'd have to always subtract 1 before we did the multiplication. Starting the indices at 0 means we don't have to do that. So we can just substitute the array index in here. Because remember, this is 0 times 4. I probably should have written that out, but I didn't. So one of the things that arrays are really good at doing is retrieving elements if you know the index. So if we know the index of the element we want, we can get to that element very quickly, regardless of where the element is in the array. Okay, so now we understand how arrays are stored under the covers, and we understand why when we have an index of an array, we can get to the element really, really quickly. Doesn't matter where the element is in the array, we do the same calculation. So with that in mind, let's move on and look at the big O values for array operations. I'll see you in the next video.